our featured speakers tonight. All right, recording in progress. I heard it, so I think we're good. So yeah, as I was saying, I'm going to be brief here. We all know Gert and Kai. They're going to tag team our talk tonight, and it's going to be an exciting one because Gert's going to talk about narrowband filters, which then feeds into Kai's talk about coloring with narrowband images using pixel math. Just a quick introduction for these two gentlemen, for those of you that don't know about their backgrounds. Gert, master's in physics and PhD in electrical engineering, and Kai, physics also, and then MS and PhD in applied sciences. So with that, I'll turn it over to you, Gert, to start the talk here tonight. Right. Thank you very much.
Thank you, Dan. And let me see, I will do the sharing. And I share the application. And if I go full screen on it, are you guys seeing it full screen?
Looks good.
Awesome. Yes. Thank you. So yeah, let's get started and talk about what in modern astrophotography, filters, especially narrowband filters, and a kind of reasonably new product of narrowband filters can do for us. The frame I'm showing here is color coding light pollution in our region, and we can almost trace the major highways and cities. And I guess if you can see my mouse here, about like Livermore got to be about here, and even Lick Observatory is probably here where that E of San Jose is, which is also the region where our the dark sky observing location is still way within this bigger area of like medium light pollution. So we have to accept the fact that we are within light pollution, and if we want to do astronomy and astro imaging in particular, we have to find ways to deal with it. So let's first look at what light pollution is out there. We are looking at spectra of different light sources, and we're seeing how different light sources put different amounts of energy, of light intensity into different colors. And we'll get back to how that is kind of laying the playing field for using filters in astrophotography. We have good old traditional things here like the low pressure sodium, which actually in the old days was almost a gold standard as a lightning source for city lights. And actually it gets like a AAA rating from Dark Sky Association analyses, because it is emitting its light in a single wavelength, which makes it reasonably easy to get rid of it by filtering it out through means that we're going to go into the talk. As you come to more modern technologies, and of course LED technology being the one that every municipality is using in their street lighting, we're finding that first of all, the coverage of spectrum broadens, and unfortunately the rating goes down. So it is kind of an unfortunate development that cities and towns are picking up LED lighting for their street lights, and everybody is so happy about it. But from a stargazing point of view, it is not an increase in light pollution, but a spread of the light pollution, making it way more hard to fight against. So when we want to take images that try to block or reduce the penalty of light pollution, we want to use filters. Now, in the good old days, who remembers like a Vratin 92 filter being used for hydrogen alpha light photography? you would have a glass or even like a film type of substrate, and that will be a filter. You would have recently, well, developed filters that are called interference filters. Most astronomical filters today are interference filters. And if you get one of these little round filter glasses in your hand, you want to know what it is. If it is like one of these shiny reflective coatings on it, you probably have an interference filter. How do all these filters work? Well, color filters, basically colored glass, has been around for 1,000 years. You find the old cathedral windows basically being colored glass. You put in colored dyes into the material. They could be organic, they could be anorganic, and you get colored glass. And you have some colors that are allowed to pass and some are blocked. You can have dyes in the filter that allow wavelengths longer than a certain threshold to pass. You call that a long pass filter. You have a short wave pass filter, allows you to pass on wavelengths that are shorter than a certain wavelength. You can actually combine them and you get what is called like a band pass filter that has like a transmission maybe from 500 nanometer, which is in the yellow, to maybe 600 nanometers, which would be close to red. Interference filters are, I think, a post-World War II invention where you are using the interference of light. What is happening? You have a glass substrate on which you have layers of deposited materials that will have transparency in the spectral region, but the interfaces reflect light. As much as the first surface reflects light, the border line between the first surface and the next type of material reflects a piece of the light. And these, let's say the top surface is denoted by this little blue arrow here, and the next surface down reflects a little bit of light denoted by this orange here. Blue and orange are not supposed to be colors of light or anything. It's just denoting these are two different rays of light that are reflected back. And two different rays of light coming together, they interfere. They can interfere adding up their waves of light in a positive way, then you get a propagation of the light, or they can interfere what is called destructively, where you do not have propagation of the light. So if the yellow and the blue have a condition where they're destructively interfering, which is given by the thickness of the layer and the wavelength under observation, they cannot be reflected. But where the hell do they go? And well, we have conservation of energy. They have actually to go into the material. So for example, these modern anti-reflex coatings that you have on your glasses or your binoculars work this way, that normally on a glass surface, you would have 4 to 5% of the light being reflected back. But even though you have your first surface reflecting actually 4 or 5% back, the next surface contributes 4 or 5% in a destructive interference, and the light has no choice. It cannot get reflected. It has to go into transmittance into the glass. Now you can stack several of these layers in your deposition of thin films onto your substrate, and you're getting conditions where you have multiple wavelengths of light that are not permitted to enter the glass, that are reflected out, or that are transmitted. And so you have maybe a single wavelength or a kind of range of wavelengths that you transmit through, and the rest is reflected back. So how do we use those filters in color imaging? Well, starting with like a DSLR, like your Sony, Canon, Nikon camera, or color astro camera, could be CCD, nowadays probably CMOS. You could use no filtering at all. We're going to see an example in a second. Now, being a color camera, the camera itself produces color data for you. You don't need to take any extra steps to produce color data. So you could still filter the incoming light into your telescope with either light pollution filters, that will be interference filters that are blocking maybe the light of a sodium light, or maybe a maximum emission light from an LED light source, whilst maintaining transmission of maybe like a hydrogen alpha for a nebulosity, so that these come into your color camera and create a signal that you can get as an image. You can also have black and white camera, but then to produce a color image, you will have to take sequential images in red, green, and blue filters. These are usually broadband RGB filters, so they capture the entire blue and green and red spectral ranges. So instead of a single, what they call like a one-shot color imaging, you will do like a multi-exposure, and then in post-processing, produce your color. And the relatively new method of using a narrowband filtering, like for example, those colors that the Hubble is showing their images in, where you have single wavelength narrowband filters combined with a black and white camera taking multiple images that you then combine. Let's look at a couple examples. This is kind of what you get when you try to shoot a picture of the Andromeda Galaxy with light pollution. You hold up your Canon, your Nikon, your Sony, you put a little telephoto lens on it. It accepts all the colors of light coming in. And that means light from the background as much as light from the object. These light sources mix and result in an overall low contrast of your image. You will lose signal to noise that you cannot even recover with processing. So with light pollution, and one-shot color exposure is probably going to suffer. Now, going to a darker location and maybe an RGB multiple color channel exposure, you can then process those into a color image. Remember, you have to take images like 3 times as many. You have to take red, green, and blue channel images and process them together through some computation that later on Kai will go into as well, to produce your color image. In this case, it's a very simple red, green, and blue image combining into a color perception the way we know it, for example, like from color photos or color TV, where similar principles are applied of combining red, green, and blue light into something that we perceive as a color image. In the broadband image, for example, of such type of an object like a galaxy, where the galaxy light occupies basically all the spectrum, you can suppress some light pollutions from coming into your camera, coming onto your sensor, but you're better off going to a darker location where by choosing a absence of light pollution, you're reducing its impact on your image. Now, narrowband imaging, yet again, uses this approach as we've seen in RGB. Now, only you're not using what was in RGB, like broadband filters to capture broad spectral red, green, and blue. You capture images in very narrow frequency ranges, wavelength ranges of the spectrum of light. You could choose them randomly. Now, we can be smarter than that, and we can choose wavelengths that are preferentially emitted from our astronomical objects, from our targets. Typical wavelengths of light related to the elements that they emit them would be hydrogen, where we have hydrogen alpha, oxygen, where we have a ionized version of oxygen, oxygen 3, a double ionized oxygen atom, and sulfur 2, a single ionized sulfur. And rather arbitrarily, we're assigning a color of our fundamental RGB colors to each channel. And then we combine them the same way we would do with an RGB image. But we have to remember that even the combined image, it looks colored to our eyes. It is what you would call a false color image. If you would have a super spaceship and superhuman eyes, and you would fly next to the Rosette Nebula, this would not be how it would look like. It would look different. This is a representation that I think the folks in Hubble had developed to color encode the presence of these elements in space in the object, and also their energetic excitation levels, so that when the astrophysicist sees that image, he or she can say, okay, there's a lot of energy, there's lesser level of energy, there's the least level of energy, denoting by the color of that image. Okay. Now, pretty recently, we came to a combination of available filters that basically are narrowband filters, but instead of transmitting a single wavelength of light, like in the previous image, we would have one filter for hydrogen alpha, we would have one for oxygen, and so on for sulfur. And you would have to take multiple images and combine them in post-processing to achieve the goal of a color image. With the development of more advanced multi-wavelength narrowband filters, you can take your color camera, your color DSLR, for example, or your color CMOS or CCD camera, and apply these multi-wavelength narrowband filters. As they're only very narrowly allowing light from around these spectral lines, our desired spectral lines, to transmit, the amount of light pollution is significantly reduced. We're suppressing the background light pollution. We're selectively collecting the light from our target, from the emission lines of our target. So the suppression of background and the selective transmission, that yields a high contrast. And it allows folks to take, like from my backyard in Fremont, an image of the Eagle Nebula in all the detail of hydrogen alpha nebulosity, yet in a single color, in a single shot, capturing the colors that make up this color image. Now, looking around, what filters are there? And here goes a shout out to our local friends of many, many years back. Were in the 80s, Lumicon, the company that Jack Marling started here in Livermore, produced interference filters, bandpass filters for visual and for some photographic use. And we are seeing that we're looking at the transmission spectrum of one of these earlier filters, and we're seeing that some of the spectral lines that are denoted here by these dashed lines, they're the engineering of the filtering of particularly these layers of interference material in their deposition is done in such a way that the interference of different thicknesses of these layers and their refractive indices allows light to come in these band passes. And they could be wider, like this one here, the Lumicon Deep Sky filter, and that could be used for visual observation because your eye needs some light to see something. Or you could have a narrower band pass like this one, where the green here denotes where the the hydrogen beta and the oxygen 3 lines would be in the kind of blue greenish part of the spectrum. And you would allow those lines that are mainly coming from nebula emissions, for example, in hydrogen and planetary nebulae, to be transmitted, while the light next to it that would be coming maybe from street lamps, actually in those days it would be mercury or sodium street lamps. And you see how nice the spectrum here goes down to almost zero, which is where in the 550 you would have the sodium lights. So you would be able to basically click off the sodium lights and see your nebulosity. You would have the hydrogen alpha lines here by 6,500 angstrom, 650 nanometers, that would be transmitted here in the deep sky filter, but in the visual UHC you wouldn't see it a lot. There were several more over the years. You could get like Orion and Celestron. They would call these light pollution rejection filters, and they've been around for quite a while. LRGB filters that you would have for RGB composition photography with the black and white camera would look a bit like this, just color filters that have very well-defined band passes for the fundamental colors, red, green, and blue. And you would also want to watch out that they are ever so narrowly overlapping. So you would have a little bit of a handover from something that was like not like exactly blue, not exactly green, but like somewhere in the middle. And actually some lines like the oxygen 3 line actually almost falling into this. So they will be just barely captured in the blue, just barely captured in the green, and then they make this sort of turquoise color when you combine them. Narrowband filters are just allowing transmission of certain spectral lines, hydrogen alpha, oxygen 3, hydrogen beta, and you would use them combined with a black and white CCD or CMOS camera for narrowband imaging, yet again, collecting light over multiple exposures and combining that in post-processing into a false color image. You could have images from additional wavelengths like methane, for example. If you want to observe Jupiter, there's some interesting methane emission from Jupiter's atmosphere or hydrogen beta. Now, a recent innovation would allow you to actually combine multiple of these transmission windows onto a single filter. And that's what you would call these multi-band filters. Here are some examples. And we're seeing here a filter that you would call like a, maybe a dual band, because it has two transmission humps in the spectral line here. The left one here at the shorter wavelengths includes hydrogen beta and oxygen 3, and the one here in the red is centered on hydrogen alpha. Now, again, there's a little bit of a marketing speak. As you are actually capturing 3 spectral lines within these 2 bands, they're telling, okay, 3 is better than 2. So they're calling them tri-band narrowband filters. Although I have not seen a filter that has as a, like its spectral fingerprint achieved like to isolate between hydrogen beta O3 and then yet only captures hydrogen alpha. Now, you may have filters where you forego, for example, the hydrogen and just have like a dual pass band where you have oxygen 3 and hydrogen alpha. And you sort of play a little bit of the game in post-processing that you're saying, okay, this here falls as much into the blue as it falls into the green filtering or the green color perception. So you're mixing your assignments of red and of green and blue into oxygen 3 here. And actually recently, a filter has come out that actually catches 4 wavelengths here, the blue, hydrogen beta, the greenish oxygen 3, and then actually 2 transmissions in the deep red, the first one being hydrogen alpha and the next one being sulfur. The more of these transmission bands these filters get, and the narrower these transmission bands get, the more pricey they get, and the more difficult to manufacture. So you can call this like the battle of the bands, of these transmission bands in your filters. In essence, you have 4 desired spectral lines, and they come in 2 groups. You have the blue-green, which is hydrogen beta and oxygen 3, and then you have reddish, which is hydrogen alpha and sulfur. You can make 2 spectral bands that are, you would call them a dual band, and you would include either O3 and H alpha, and there's this Optolong L extreme filter that does that. You eliminate a lot of light pollution, but you forego hydrogen beta, which is next to O3. So that filter already shuts down for hydrogen beta. You could combine oxygen 3 and hydrogen beta in one band, and then have hydrogen alpha, which is like this L-enhanced filter or triad tri-band filter that are in the market today. I'm not aware of a true tri-band filter to close the gap between O3 and hydrogen beta, but maybe one comes out. And then there are what's called like quad band. Of course, that is the top of the marketing pyramid, 4 narrow band passes, and of course these are very pricey filters. You pay about $1,000 for a 2-inch filter piece of glass, so don't drop that. Now, folks have gone out and taken these filters and done some measurements. So you have like a large list of these filters, and you see how actually, even though they're advertising all claims, oh yeah, we are like a dual band or a tri-band filter, we're enabling you to do astrophotography from light polluted areas, you see slight quality differences. Like, for example, you have some here that capture the hydrogen beta. I've marked the hydrogen beta blue line here. There's the oxygen 3. That's also the desirable line from planetary nebulae. And then there's Mercury here, which of course you want to block. So this one should all filters have down at 0. And for the desirable wavelengths of hydrogen beta and oxygen, you want to have as much transmission as possible. And you'll see some of them, like for example, this orangish one here, which is like some here, what is it, STC dual narrowband. They decided to forego hydrogen beta and focus on like just the oxygen transmission. And some may have like maybe a little cut back here, like this, what is it, this gray, what is it, like the Mead. It's a filter from Mead for oxygen 3. It allows some hydrogen beta. And then you have some that are really nice and steep. They go up to like above like a 95%, and they catch hydrogen beta O3. And then they go nicely back down and lock up for hydrogen, for mercury. And you have similar kind of eye chart curves for the red transmission band region, where you have a hydrogen alpha, you have the sulfur, and you can see some are extending their transmission to include sulfur, some are not. So for example, the Optolong L enhanced, the blue one, goes down here. So that one makes only a nice run up to get about 89 or 90% of hydrogen alpha, and that's it. Okay. Now, what happens when we run these filters, these narrowband filters, in a telescope that may be a very fast F ratio lens? You have a dependence actually on your F number. What happens is light passing through a piece of glass gets shifted, and its angle of incidence on the glass, here it is a 90-degree angle, it could be a different angle. And as the projected length of light passing through, let's say, a layer of interference material on your substrate, let's say this is your deposited thin film of a particular index of refraction, the little red arrow here is a longer arrow than this arrow. So the interference condition for the light on the other end of the filter is different, and meaning that you will have a slight shift in your transmission shape, in your spectral shape, depending on the angle of incidence. And so, for example, an angle of 14.89 degrees, about 15 degrees, that's about an f1.8 photo lens, if you think about the angle of light coming from your lens. And you see a certain shift here. And the blue line, the blue transmission profile is about an f2.8 lens. And then you're coming to the more like an f3.3, which is where basically like your rich field light gathering telescope would start. And you translate that into transmissions for different of your desired spectral wavelengths. You find that, for example, this here is like a simple dual narrowband narrowband filter, that your sulfur is out of the picture anyway. But at an F2, you're starting to see that some lines here of nitrogen are actually no longer at peak transmission. They go down. You see it even more strongly here with the L-enhanced filter and the OPT radiant. Why is that so more noticeable? Well, these filters have very narrow transmissions. If we go back to the chart here, you see that these guys are the ones that have what you would call like the better suppression of light pollution, because they're so nice and narrow. But that comes at the price of losing at stronger F numbers to your condition of the filter to transmit light becoming no longer ideal for the desired wavelength. So your interference condition gets penalized, and you get only maybe 50% of oxygen 3 still being transmitted at an F2. So you want to be careful to go with these very narrow band images. For example, if you use like a hyperstar optics, where you use like a Schmidt-Cassegrain and replace the secondary mirror with a piece of optics correctors, and then directly image in the native focal length of the primary. So when you do imaging, you use your black and white camera. You can use a filter wheel with RGB or narrowband filters. You may need to refocus after a filter change. And you will, of course, use an off-axis guide or a guide scope. Single filter for color cameras. You will use a color camera. You will have one filter in the light path. You will have one focus settings. Still, you need guiding and a guide scope. How does that setup look? You want to have maybe a photo lens. Here's your camera. Here's your bayonet adapter, which this one has a thread on the inside to accept the 2-inch filter, and your photo lens, regular commercial photo lens. This is how you plug it all together. Usually you have that piggyback on your telescope, and you use your telescope, for example, for guiding. If you want to use it for a scope, you start again, with your camera. You have maybe you probably should have an off-axis guider that is combined with the filter drawer mechanism, where you can put your single filter into a holder and slide it in there. Have your 2-inch adapter piece. Mount it all together, you get something like this that you plug into your telescope, having your guide camera, off-axis guide camera here. Now you go out taking images, so you must select your target. You want to have targets that are dominated by emission lines. Something like a globular cluster or a galaxy will not be working well. Reflection nebulosity that is also reflected multispectral starlight doesn't work well. Pleiades is a bad idea. Trifid nebula may be marginal. It is great for planetary nebula, ring nebula in Lyra, supernova remnants, Dale Nebula, Crab Nebula, and these huge hydrogen clouds, Orion Nebula, Lagoon Nebula. And I'm showing a couple of examples here. This is an image I've shown, I've taken from H2O, North American Nebula region. That is with the L enhanced filter. And here on the left, the Eagle Nebula. Actually, this is from Fremont, through light pollution skies. And of course, with some darker skies, you can do the Veil Nebula. Simply, I shot it from H2O because it is behind the overhanging roof of my patio from where I live in Fremont. So I took that image over there. So these are the types of images you can take with these filters, one-shot images. You don't need to work your way through RGB or multi-image combination and post-processing, and you can achieve some nice suppression of the light pollution. So I think that is the last slide from my series. This is the end of part 1, and for the more advanced topics, I'd hand it over to Kai. So thank you very much, and Kai, pick it up.
Thank you, Gert. Let me share my screen. Let me see. All right. Can you see my screen?
Yes.
Okay. Let me get this started. All right. So I'm gonna follow up on, now that we know about narrow bands and what kind of images we can get, I'm going to kind of go through what kind of processing we do to make it look good. So my journey into this is when I started looking into narrowband images and trying to figure out how to make it look good. I started coming with a lot of tutorials on how to mix them, and then I came with people using funky formulas in PixInsight to mix them, and specifically this right here, these two. And I say, let me go back, sorry. I say, what the heck are these? So I'm scratching my head. It looked Greek to me. So that's how I got into rabbit hole. And I'm hoping by the end of this talk, we get some insight into exactly what these are and why we use it. I hope this is going to be more interactive. So if you have questions or need some clarifications, please chime in, okay? All right, as Gert was mentioning, narrowband coloring, humans are really custom looking at RGB images, just wideband, blue, green, and red. But narrowbands are focusing on very narrow bandpass images that are imaging images from emission line from O3, H alpha, and S2. The thing is that, as you notice, the H alpha and S2 are both in the red. So if you're magically able to come up with 3 different images, one for each, and you want to look at them, the H alpha and S2 are the same red, or kind of red. Unless you have very, very acute vision, it's very hard to differentiate. So when you look at it, it's just red. And then the O3 is in the bluish green. So if you want to represent all kinds of different emissions in a 3-color world, it's impossible. The other thing I want to highlight is that H alpha emission is typically very strong compared to others. Let me give some examples. So these are some of the screenshots or an image I took of the H alpha of the Hard Nebula. This is H alpha. So give you an idea of the difference in terms of magnitude between the 3 different wavelengths. This is H alpha. This is O3. and this is S2. You see the difference? It's, if you combine these three images together, H alpha will dominate everything. So when you put it together in 3 channels, your image will create just a red heart. You won't see colors that you typically see. So that's one reason I'm actually interested into narrowband coloring, because it actually opens up the artistic side in us. So we can come up with images like these. And I said, my God, how did I come up with these? So you can see blues, you can see all kinds of velocities all around. You see different color representations, and they're all acceptable in a community. This is where I find it very interesting. So I want to start diving into how we get to these. So to do that, let me kind of go through some basic idea how color are represented in the software that we use called PixInsight. You can use other software as well, but they do pretty much the same thing. All colors in RGBs, they're ultimately just numbers in the image. In PixInsight, the numbers, the color are represented by numbers from 0 to 1. So for example, if I go to here, so if you can get an idea, if I have images, if I have an image that I go from dark to white, white to dark, if I try to combine these 2 images, I can do quite a bit of different mathematical computations. I can do a minimum, I can multiply them, and I can do a whole bunch of operations. If you know about Photoshop, these are the type of blending mode you can actually use to combine layers. So remember, our 3 colors are just layers, and I'm trying to combine them. So if you want to know how to combine these in a whole bunch of Photoshop layers, this is the page to go. This shows you exactly what to do if you want to do darken, multiply, color burn, linear burn, a whole bunch of things. These are the mathematical instruction to do that. For example, multiply is simply multiply one to the other, and others. And let me give you some more concrete examples. Let me go back here. So I want to highlight three different types. If I want to combine 2 images, I can do a linear combination. For example, if I want to, so I want to combine some red and some H alpha. Let's say I'm going to combine images to make a nice Andromeda galaxy image. I can combine a little bit of red and a little bit of H alpha. And remember, these are numbers representing intensity from 0 to 1. So I need to just do a percentage of 1, and then the rest, the others. So A and B, if they combine to 1. So that's a linear blend. So you can see here, you can combine from 0 to 1 like that. There's another operation you can also do. You can also multiply these 2 numbers together. So what happened is that, if I multiply, you would see the differences. It kind of gives you an idea that if multiply gives you a number, it's high only if both of these numbers are high. So for example, if I have a very high region of red and a very high region of H alpha, then to multiply those numbers together, it gives me a very high number. But it gets less and less over time. It's actually non-linearly dropped. Screen is actually a very interesting way of combining 2 images together. Mathematically, it's just this, but I actually want to kind of go through this. Screen, it helps you combine 2 images together, but it doesn't overpower 2 images. I'll try and go through an example here. A screen image is simply this formula. But what is this formula? This wiggler thing is actually the inverse, the inverted image of that. Image of that is just 1 minus that, meaning that if it's high, it'd be low. If it's low, it's very high. So it's the inverted version of the image. So if you invert an image, that's what it is. If you actually multiply that together, invert of R, this is red channel, and invert of H alpha, essentially what this become, if you multiply that together, it's actually simply come up together. It's simply just the red plus the H alpha minus this combination. What it is telling you is that I'm combining the red and the H alpha together, but I'm subtracting a little bit where they both are together. So if, for example, if I have a region where both are very red and very has a lot of H alpha emission, if I combine these two images together, if I do it together, I'll double the amount, which I don't want, because if I double the amount together, it oversaturates. So this is a correcting factor to kind of drop off the combination of these images. I'll give you some example what this means. Let me kind of give you the demo. Let me get that here. So this is the Andromeda galaxy image I took in my backyard. It's like a 3-hour exposure. It's using a one-shot camera. It has both RGB. This is an H alpha image I took from using an H alpha narrowband filter. If you noticed, I kind of combined together. There's a little difference in here. Remember, the RGB, the color image of the Andromeda is made of the R, the red color, the green color, and the blue color. All right. You notice that each color has a little different structure. So this is blue. This is green. And this is red. Now I want to focus in red. A lot of people, if you see the Andromeda galaxy, this is what people usually see. This is the Andromeda galaxy, where you actually combine the Andromeda galaxy in RGB, plus also the luminosity, the nebulous data from H alpha. You see these popcorns right here? These are essentially nebulas in Andromeda galaxy. And I get these data from my H alpha image. Let me kind of go back. Let me explain what I'm talking about. So this is red, but this is what I got from my H alpha filter. You see the difference between H alpha and red? You don't see the popcorn. The popcorn structure is not very prominent in here because the H alpha only emit in a very short wavelength. I mean, very, very small range of wavelength. But because I'm focusing on collecting data on that wavelength on the H alpha, you see all the structure. So my goal here is I want to combine this image, but I also want to add my H alpha data to it. So if I want to go from this image to this, to this image. You see this, the red part? That's what I'm talking about. I want to combine colors. Now, I'm not talking about, later on I'll talk about the nebula combination, but I want to highlight that you can also use these narrowband to actually accentuate images from your wideband images as well, because you can actually add H alpha data to this. And I thought this was really cool because you can rethink if I was actually in Andromeda galaxy, these are actually my nebulas. I'm actually seeing the Heart Nebula maybe here or something like that. Every one of these is a nebula. It's amazing. And I can actually overlay that. So how do I do that? So that's what I'm talking about. I'm trying to combine a red image, right? Remember, I have a red image and also have my H alpha image. So that's what I'm talking about using the blending mode that I just talked to you about. So how do I blend together? So I can blend it by using linear blending. I just add a little bit here and a little there. So that's what I did. So let me kind of show you how this is done. Now, actually, another cool thing is that, remember I told you there is the multiply operation. What multiply really does is that it would, remember I told you it won't show up if both the red color and the H alpha color are present together. Remember, if the numbers are high, only if both sources are high. If one source is high, one source is low, the combination and multiply the product of those is still low. So I can use that information to actually say, aha, how do I find nebulosity where I have both that information from my H alpha data and also from my R data. Remember, this is my R. Let's go back. This is my R data, and this is my H alpha data. I want to isolate only the nebulosity. How do I do that? I just simply multiply. So to do that, let me kind of get to pixel math. Let me kind of move this here. Okay. So all I need to do is I need to multiply. Let me try to get that. I'm multiplying HA multiply to the R channel. Remember, I'm just multiplying two numbers together. See what happens. Oh, hold on a second. You need a reference. Oh, sorry. Case sensitive. There it is. So I multiplied those two numbers together. What happened is that the nebulosity, it's get accentuated here. Remember I told you when those two numbers are high, it'll show up. If one of those numbers are low, it will be less show up. So this image tells me where the nebulosity is in the Andromeda galaxy. All right. Now let's say I want to combine these images. So what I can do now, I'm going to do this. Now I want to combine both my RGB from my Andromeda. I also want to combine it with my H alpha data. So how do I do that? So with pixel math, all I'm doing just a blend. In the red channel, this is what I'm doing. The red channel, I'm combining 70% of my H alpha and 30% of my red. All right? Am I green? I'll just green. Blue? It's just blue. Remember, H alpha is red, right? H alpha in the red zone. So all I'm redoing, I'm adding emphasis to the H alpha data and less emphasis in the R data. If I do that, watch happens. This is what you get. So all I'm really doing is I'm combining the red channel adding 7% of the H alpha into my channel, leave the green and the blue alone, and lo and behold, I get my Andromeda galaxy, but I got these red pops. That's how we blend. And that's when you start playing with math and playing with numbers. So after this, you can do a whole bunch of curves and stuff to accentuate this red even more. But look at the difference. I start with my Andromeda, right? Not much red, to this, simply by just blending in H alpha. All right. So let me kind of go back to what I just kind of mentioned before. All I'm really doing is that I can blend different channels of data using linear blend. Again, I'm mixing R and H. As long as combination is kind of get back to 1, I'm just combining ratios, right? Now remember, I also show you how to accentuate where both sources are similar. I simply multiply. If I multiply, then I get images where they both exist, accentuated. That's why I multiply here. You see, the only thing that's white is when both sources are high. Everything is kind of gray. Screen is another interesting thing, is that when I combine 2 images together, if I combine 1 and 1, I don't want it to be 2, because if it's 2, that's too high, because that blows things up. So this really does, this screen function is simply, it adds the 2 sources, but it drops off a little bit. If they're high again, it kind of offset it back, so it go back to a more natural state. That's why when you see a screen mode, when you combine it, you don't see a very bright spot. It's still kind of naturally smooth out. That's why a lot of image processing people, they combine these images in these screen mode. It's very smooth. It doesn't have a sudden jerk up. It's just natural. So these are typical blending mode, and we're going to use it over and over again in this talk. All right? Is there any question about that? Okay, let me go back to my next slide. So let me just, okay, now I'm going to go to my next part of the talk, is now we're going to talk about actual true narrowbands. Before I just talk about how to add narrowbands to RGB data. Okay, let me get that started. Is there any question before I load in my next project?
Hi, do you have examples of the Andromeda that was using those other combined techniques other than the linear?
I have both. The images we get from the camera is always linear, so I have the source image for those, and then the nonlinear ones are the one I stretched, and so I have those as well.
Okay.
If you guys are interested in playing around with this, I'm more than happy to share my data. All right, so this is loaded. So the other thing I want to highlight is that the one reason why you see people use narrowband, you saw the Andromeda, the RGB data is kind of noisy. It's quite noisy, actually. I took it in my backyard. It's a 3R integration, and with all the noise, light pollutions, it's really bad. But I took time to gather my Heart Nebula. So this is a 7R integration of H alpha with my f4.5 rig. So you see, so this is stretch because it's more for example. I want to show you how we're going to combine these images together. All right. So I kind of mentioned to you, H alpha is dominant. It has the most detail. This is O3. It's stretched a little bit more. Typically, you won't see this detail. This is also like a 7R integration. You see the structure of O3, and this is S2. Now, I want to kind of walk you through the structure. The reason this is important is that this is give you that when you combine these layers together, when you see all those nice structured RGB, the reason you see all those ridges and colors is because the structures are different from all these three. But there is a pattern. So you notice in S3, S2, there are kind of thin lines. They kind of follow the outline of the red of the H alpha here. S3 is more like people like the concept of like surfing on a wave. The S2 is more like it's like breaking the surf, the white fluff. That's why you see a lot of the false color representation you see in white, because people are used to seeing white in surfs. So a lot of people kind of follow that. Whereas O3, you don't really follow that structure, but you see there's a blob of O3. That's why in the heart nebula, you see a blue part of the heart, and that's where it's from. And our job here is, how do I make use of these three images and combine it into interesting images? So Gert was talking about Hubble palette. So what I did, so this is combining this is HO palette. All that really does, I'm not doing any pixel math here. All I'm really doing is that the red is H alpha, but the blue and the green is only oxygen. Now let me explain what we're seeing here. You see, remember I told you the oxygen is mainly this blob right here. So the fact that I'm combining both oxygen in both green and blue, but also the H alpha also has data in that same region. So when you combine, when you have region where you have data in both R, in red, green, and blue, what do you get? You get white. That's why you see white, and that's how people can see the white surf. So here's an example of HSS. So same thing here. Remember I told you the S2 is really follow the ridges of the heart. So the fact that I'm using both S2 for both green and blue, and of course H alpha has red in the same region. That's why you see all these white. This tells you this is where the S2 are, all these white areas. So this is kind of cool stuff. It's kind of interesting to show you where are these emissions relative to the nebula. All right. Oops. Here is a HSO. This is where I'm combining three of these palettes together. Now I'm not doing any math here. I'm simply just, this is H alpha for red, S2 for green, and oxygen for blue, okay, RGB. So if I combine that together without too much, because I've kind of pre-stretched those three frames, just by adding these three together, I get these images. So kind of give you a basic tenet in these. If you have really good data and you stretch it okay and you clean it up, it's pretty easy to get a pretty good representation in false color in these Hubble palettes, just by simply combining them. All right, but but since this talk is more about pixel math, why do we do that? So here, this is a product of H alpha and S2. Remember, a product is product of those two images. It tells me where both S2 and H alpha exist. See the ridge? So kind of give you an idea of where they are. I can do the same thing. Now, this is the screen function. Remember I told you the other blending mode. This is where I'm combining the H alpha and S2 in the screen mode function. It's, remember which H looked like this, and S looked like that. Ooh. So screen function is simply just combining these two layers in a way that does not overpowering, but it kind of gives you combine together. All right. So let's have some fun. Let me go to here. Okay. This actually, yeah. This one is image with a whole bunch of these mixing modes together. So in here, I'm mixing. You notice that this is, by mixing it, I see blue automatically here. It's hard to see blue when you combine all these colors before. Remember, when you see these colors, you see all kind of magenta color. Magenta colors because you get H alpha combining with other, so you get red with combining other color. So you always get these magenta or green or yellow color. You never see pure blue. But how to get pure blue or more and more blue? So this is what I do. So in the red, so in blue, I have blue, all right? But in red, I use this formula. Now, what this, remember, what this really is that I'm doing a linear blend of two images. I'm blending S2 and H alpha. But when I blend, I'm not reblending with the ratio of a integer of a float number. I'm actually blending by the intensity of the oxygen in that pixel. So these are called dynamic blending. So I'm actually blending within blending. So the oxygen would dictate how I'm seeing things. So what I'm doing here, let me kind of explain I'll kind of give a high level what this is. All I'm really doing here is that for the red channel, I want, if the oxygen is a lot, I want the S2 in that pixel. If there is not a lot of oxygen, remember this is inverted images of that oxygen, then I want H alpha. All right. Remember, this is just inverted that. So by doing that, I can actually take a lot of different ratio using an image to drive me the ratio. So instead of just doing a simple 30% to 70%, I'm using a mask or an image to actually dictate how I'm blending. So by doing things like that, I can go ahead and create all kinds of things. All right. So you can come up with a whole bunch of different combinations of colors. Remember, color is simply different mixing of different RGB together, different values. And to come with these numbers, because each of these channels are numbers anyway, so I just use it as a multiplying factor. So that means now I have an infinite solutions to do any kind of images I want. I remember I kind of give you an idea that if you want to identify things that are two emission together, you just multiply, or you want to just do either or, you just use screen. So there are different blending modes to kind of like an artist. Now you can mix and match to kind of come up with your own creation. All right, don't want to go too far on that. The other thing I want to kind of highlight, let me kind of go to here, jumping a little bit, is I want to kind of, let's just say that I have only two filters. I don't have the S2 filter. I only have H alpha filter and O3 filter. But I want all three colors. How do I come up with colors, right? So, so there are several ways. I kind of give you an idea before. I can just have, I can just double reuse the second channel to my third channel. Remember, I have H alpha for red, but I use O3 for green and blue. By doing that, now it gives me the white accent where they're all together. That's why you get those white the white outlines. Another thing I can do, I can actually create a totally synthetic channel by simply combining two of these filters together. This here, R is H alpha, blue is O3, but instead of just using O3 for my green, now I'm doing multiply. I'm just multiplying these two images together. Remember, these multiplying will give me a idea where they both exist, and I can multiply by factors to make it look better. So now, lo and behold, instead of just two channels, I come up with a brand new third channel simply by using one of these blending modes. How does that look like? Let's see. Let me go to PixInsight. Let's try a new one. So I told you red, I want H alpha. Blue, I want O3. But green, I just want H alpha times O3. And let's add a factor to it, right? Remember, I'm only using two channels of data here. That's what happens. So by using just two channels, I now come up with a brand new color image that look like three channels. I can use a whole bunch of different blending mode to come up with anything. Okay? So that's the idea about pixel math, is that you're not limited by just the image you collect, but now you can use the image to overlay other images and blend it in any way you want. But you multiply, screened, blend, just linear blend, whole bunch of stuff. So that's the basic idea about these artistic idea about coloring using pixel math. It's very powerful, but the ultimate idea, the thing you have to watch out for is ultimately each of these images, each of these data you collect, it's just numbers. They just 0 and 1, 0 to 1. So if I pick any pixels, you see the K number, that's the intensity. From a star very high to a dark space very low. They're just numbers. So now I can play with numbers to create brand new channels. So that's how you can create synthetic blends from thin air. So that's how you can go from 2 channels to 3 channels. I can actually go from 1 channel to 3 channels. We'll go through that. All right. Any questions? All right. So now that I kind of give you an idea of what I did before. So now, yeah, okay. So, okay. So typically if you, after processing, there are a whole bunch of post-processing that can even look better. You can, if you into color these processing, you just add luminosity to RGB to make it even pop up in detail. You can actually saturate and actually accentuate the color by curve transform. I mean, there are a whole bunch of tools, but I don't want to go through too much in that. But basically is that once you get the basic structure, now you can actually do a whole bunch of other stuff to make it even look better. So that's why the sky's really the limit of how you come up with the images. All right. Now, I'll just finish up into 3 different things after that. These are more advanced pixel math stuff. But so raise question if you have. These are things that I've been playing around with. Now, I kind of mentioned you can mix and match these frames by blending or multiply. But there's actually another way. It's called exponential functions. What is exactly exponential functions? Okay. So when you see an image like this, you can actually stretch it. Let me give you an idea. All right. So let's just say this is my original image, my heart, H alpha. And this is my curve. This is my linear curve. I mean, it's a flat line. That means it's just, I'm not doing anything. But watch what happens if I do a S curve. You see how it brightens up? Like that? You see this curve, it's a nonlinear curve. I can make it brighter. I can make it dimmer. Anything I want. All right. So in math, this is just a math, just transformation. It's just transforming from one image to something else using a curve. So that's so 2 things I can do now is that I can create starting from an image. I can start from this image. I can create a brand new image by just doing this, right? So instead of let's just say I have one channel, I own the H alpha. But if I can do this kind of transformation, I can create 1,000 different frames, images based on H alpha, but not exactly H alpha. So now I can use this to combine into my RGB image. So I can actually do that. So a class of things transformation I'm doing is, so there's a 2 that is kind of pretty well known. One is, this is actually just the screen image, the screen transfer, meaning that I'm essentially I'm combining, but then it taper off back to 1. Right? It's more like this. It doesn't keep on going. It always kind of level at 1. Here's another way. There's another operation. They can actually drop it off. At the beginning, you kind of brighten it up and then drop off again. These are well-behaved curves because at the end, it's still end at 1. It never blows up. You always stop at 1. But it changes the value. Instead of just being flat, it actually kind of sharpens it up. And mathematically, it's just this operation. So the first one is just the screen function I told you about. The open screen is simply just the 2 numbers, the 2 images subtracted by the product. The second one, this one, is called power inverted pixel. It's simply the first image, you raise the power to the invert of that second number. Now, if I just replace B with A, I can do the same thing. So A raised to tilde A. That's what I just did. I can actually use one image, create a brand new one. So that's, let's see if I have that here. Yeah. So give me an example here. Let's just do that now. Let's pixel map. Let's just say I use H alpha for red. Let's say I use the screen function for, let's say, HA race. Okay. This is that second exponential function. Let's do the same thing with this one. Let's see what happens. So by doing that, I have a brand new image. It's not very exciting, but you get the idea. I can just simply combining which alpha, but with H alpha. Look, in here, this looks like one of those dual band or tri-band filters. You see the white star, relative white star. You see dark background, and you see grades here. So I can actually create from one filter to RGB images this way. All right, and let's see. Yeah, I don't want to go through too many. I think I may be running out of time. The other thing you can actually do if you're more into PixInsight, you can actually use mask, because a lot of time when you actually do these transformations, a lot of time you want to protect the highlight, because a lot of time you just want to expose or accentuate the noise, the light details. But if you're a bright star, I don't want to touch it. You can actually use mask, and you can actually use mask by simply things like this. Mask at the end is simply just the original image with a mask image. It's a multiply factor with whatever you want. I can go to more detail on that later, but if you're interested. But there you can actually use pixel map to actually simulate a mask operation when you do this blending. I'll just skip at that. At the end, these some of the references to kind of follow up and just understand from. So for those interested, I can also publish this notebook. So that's, but let's go back at the beginning. Let's try to decipher exactly what this is. Remember, I told you this is simply just the screen transform. Remember, it's the invert of the one channel multiplied with the invert of the other channel. And the invert of that, it's, at the end, it's simply just a screen function. Here, what is this? You notice that this is a factor here. I'm trying to blend. I'm blending here. I'm blending some H alpha, and I'm blending some O3. What is my blend factor? This is my blend factor. But this blend factor is the same, it's inverted that, but this blend factor is simply one of those exponential functions I just talked to you about. It's simply this factor raised to the invert of that factor. And that factor happened to be a multiply factor of those two different filters. So long story short, you can actually decipher what this is once you understand exactly what some of these seem crazy symbols, but it's, at the end, it's just simple math. It's simply multiplying and raise and doing exponentials of numbers. That's my talk. is so. That's all I have. If you have any questions, please.
Thank you, Kai. Thank you, Garrett. Awesome.
Thank you for both of them.
I got a quick question for Kai.
Sure.
Kai, do you always stretch the various channels first before you combine them, or can you work with them native as they came out of the camera and then stretch them after you combine them?
Yeah, there's actually two school of thoughts, and actually it's in here. There's the idea here is that if you have an ideals, you have a system where you're very well characterized, meaning that you use the same rig, same camera, and you know exactly the bandwidth and you know the response curve, then you're doing photon counting, right? Because at the end, you're doing counting photons. So when you do subtraction and stuff, you just be subtracting photons. So the key here with that is by knowing your rig, then you know your bandpass of your H alpha and your bandpass of your narrow band. That give you an idea how much photons coming in, right? So when you do that, then these numbers make sense because then you know what number to multiply and what to do. So for example, what this is simply, I know a typical R filter is 100 nanometer wide. My H alpha is around 7 nanometer. So these are my factors. So that, and then, but again, you know that you have to know these numbers are not really true because the response curve for your sensor is different. So it's more sensitive to some waving to others. So things like that. But when I do my Andromeda images, my Andromeda was captured, my RGB was captured with my RGB camera, a one-shot camera, using a totally different telescope. And my H alpha is a totally different system. So for me to come up with the right number for that wouldn't make any sense. So in that case, I might as well just stretch it. And when you stretch it, the key is you want to have the numbers roughly in the same neighborhood. That's one of the reasons why you see my H alpha and my O3 and my S2 have roughly the same kind of detail. Where early on I tell you, you simply take the frame images, H alpha totally dominates everything else. So there are a lot of pre-processing you want to do when you want to mix nonlinear. Make sense? Okay.
Any other questions?
So I have a question about some of the old Lumicon filters. So this might be more appropriate for Gert. So these come in these little blue boxes, and this is a 1 1/4. How do they compare to, and this is a multiband. This one's actually hydrogen beta, oxygen 3, and hydrogen alpha. So it could be a clear piece of glass and claim this. I don't know what the stop bands are, but how do these compare to filters 20 years newer? These are old filters.
Yeah.
How does it compare to the current day filters?
They have gotten better over time, particularly the technologies to do these thin film depositions to control your peak transmissions. Like in the Lumicon days, you could go maybe, you had some that were 80%, mid 80%, some were higher. Today, you can probably go higher up in the 90% of transmission. You can also get steeper limits of your transmission band. If you want to, for example, a typical Lumicon filter or a term that they coined is the UHC filter, ultra high contrast. Well, they meant by that a filter that combines O3 and H beta. So in our terminology today, we would call it like a dual spectral line. It will be one band pass, and in that band pass, you would have oxygen and hydrogen beta encapsulated, both of them.
Yeah.
And how narrow your sides of your transmission curve would be coming close to hydrogen and oxygen on these two sides would, of course, tell you how much of the light pollution you can eliminate. But your inevitable manufacturing tolerances will have introduced some randomness on that. So I understand in the old days, Lumicon had a lot of seconds and they had a lot of rejects, and they had to carefully check each and every one of them to see which of them actually have the band of transmission not cut off either of those lines. Today, they are much better than that. Like the filters you get from, well, these companies like Optolong and these Triad filters, much better than that. Their transmission curves are much steeper. They're very narrow, and they're doing much better job at this.
Okay. So, so value-wise, how much, you know, are these a $30 kind of useful filter, or?
If you want to put them on eBay, yeah, put like 30, 40, 50 bucks on them, and maybe some person will pick it up. If yeah, I mean, you can probably go to like an online astronomy shop and see what, like, I mean, today probably what were the original Lumicon kind of flagship products would be sort of like on a mid entry level manufacturer. Like if today you would look like what Orion or maybe Celestron sell as a light pollution filter or a contrast enhancement filter, that would be what would be equivalent to Lumicon filters. But I mean, I think Lumicon is still around. I mean, their products have been absorbed into some other company, but I think some of their filters are still made. So they must have like improved on their production equipment. So they must have gotten better as well.
Yeah, so the one I held up is probably a 20, 30-year-old filter. And
yeah,
but I know Jack. I know Jack Marling, and many of us know Jack Marling. so I was kind of curious as to how well the technology continued to hold its place in
for sure. Yeah,
observing. And Kai, so my eyes are more like those of an Alpha Centaurian. So I tend to see red maybe a little bit better in my images. So you're not doing calibrated color images for a human. But I'm more Alpha Centaurian. See, my background is kind of yellow. So I tend to be that part of the spectrum. So who does color corrected imaging for human eyes instead of false color?
Oh.
You can invent any color you wish, but what would a human actually see if they could integrate?
That's a good question. I'm
That's the challenge. And then a second comment, maybe for the entire group. My concept to eliminate light pollution, since a lot of our the residential light areas now, you know, the street lighting is LED based. Why don't we turn it off 50% of the time? Let's turn it off for 30 milliseconds, turn it on for 30 milliseconds, and repeat that process. And then we as astronomers can look at the dark time, synchronize our cameras, and everybody else can use the full time, and they can see things almost equally as well as they do now.
I think the easiest solution is to switch to sodium.
Well, I'd like to see it really dark, so I would rather, you know, so the comment about sodium, one of the LICs, I think it was San Jose went to sodium, and someone down at LIC said my goodness, what happens if the aliens actually try to signal us using sodium light and we're filtering it all out? Oh my
Yeah,
God, we've lost it all. You know,
Yeah.
we're alone in the universe because everybody else uses sodium. Anyway, that's my diatribe.
yeah. Now at a millisecond of like a let's call it like a chopping a chopping period, you would have about 300 kilometers of a light travel. So you would have some phasing problems there. Let's say if you go to 10 milliseconds, you get like 3,000 kilometers of light travel distance. So
Oh.
your finite speed of light is not to be neglected.
So I actually did a system, not for deep sky, but I actually did a system where we did about 15 to 20 milliseconds of light chopping to create a dark environment in an extraordinarily bright environment at the same time. So, and it can be done. We used LCD shutters and photo flash units.
Yeah. Well, any whatever engine adjustment stroboscope does the sort of opposite, right? It turns on for a very brief period of time. If you could convince municipalities to use stroboscopic lighting for their streets, but that would make your dog walking kind of look funny.
Well, you know, you just have to get used to it because we have the priority.
Yeah, if your dog may not get used to it.
Thank you, Kai. Thank you, Gert. Thank you.
You're welcome.
I'm going to turn off the recording.